Okay, hello everyone. So welcome again to another lecture of Physics 101. So for this video, I will discuss the work and usually up to potential energy only. So work and kinetic energy and potential energy will be discussed. And hopefully we have enough time and we have enough attention to understand this new topic. So without further ado, let's discuss the outline. So the outline here, I will only discuss this up to potential energy. So we'll discuss first the systems and environments, work done by constant force, work done by varying force, and then the work kinetic energy theorem, and potential energy, and so on. Okay. So the internal learning outcomes, we have a lot of learning outcomes. I won't read this anymore, but basically this is what we are trying to to uh, to have you guys or what should you have in mind after finishing this or your what do you call this, your ability should be uh part of this outcomes. Okay, so let's first discuss the energy for systems and environments. So um matter in general has energy, and it just depends what type of energy are we discussing, and it can get quite complicated when we describe what energy is. No? So it will be discussed further down the chapter, but in simple words, usually energy's definition is the amount of potential, no, that can be converted from one form to another, or potential, the amount of energy is the amount of potential that we can convert from one type to another. And Newton's laws and principles usually are insufficient for describing this energy. So in systems analysis model, um, there are ways that we can describe energy as uh, it transverses from a boundary. So yeah, let's just discuss the system. So for a system, it could be, where is it? Why is that? What happened? Okay, so a system is a small portion of the universe, and you can define any portion of location. No, you can say that your room is a system. You can say that a ball is a system. You can say that the Earth is a system. So a system is just a portion of the universe that we can analyze to relate its energy transfer and mass transfer. So for this media, so we can see we can have an open system or a closed system, but there are different scenarios here now. So for a system, we have a boundary. So this imaginary line that encloses our system, it could be closed a system. So if it is a closed system, it is there is energy transfer within the environment and the system. So for example, the room and the outside environment, we have the system as the room, the environment as the outside of the room. And then the boundary will be the walls of the room. And this is the room a closed system or an open system? It depends. If your room is airtight, so no air can come in or come out, then it is a closed system. So if there is no mass transfer between the environment and the system, then it is a closed system. But energy can still infiltrate. So there is heat transfer through the walls that could heat, no? Or if it is hot, no, it can heat your room. Or if it is cold outside, it might cool your room through the walls. So an open system, again, there is mass transfer and there is also energy transfer. Okay, so usually we have this analysis or this way of analyzing things to help us formalize the 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 formulation of the solution for that given problem. No? So let's discuss now the work of the first thing before we discuss energies. So the work done by a constant force, for example, on a system equals the magnitude of the product of the which is F, that is parallel to the displacement magnitude delta R, and the cosine of the angle theta between the force and the displacement vectors. Okay, so I think this is a little bit. I have to redefine my definition here. It should not be parallel all the time, no. But what we are taking here into account is only the okay. We will discuss again about we will discuss the parallel thing about the work later. So basically, if you have to find the work done by a force, then you want to determine what is the distance covered by that, or actually this is the displacement, and what is the force, magnitude, and the angle between the displacement and the applied force. So for this example, let's say you are pulling a block, no? You're pulling a block at an angle, then the total work done on that block, no, assuming that it attains this displacement delta R, it is equal to the magnitude of the force times delta R times cosine theta, wherein theta is again the the deviation from a horizontal line, or not really a horizontal line all the time, but the deviation from the displacement's vector. So if we have an angle, then this will be cosine theta. If it is both horizontal, then this will be cosine 0. If it is 90 degrees, then this will be upwards. No? Okay. So knowing this as well, what would happen? Yeah. So the sign of the work depends on the direction of the force relative to its displacement. So there is a work that is positive, there is a work that is negative, depending on our force, depending on the direction of the force and the direction of the displacement. So work is positive when the force and the displacement are in the same direction. But if it will be negative, if the direction of the force and the displacement will be opposite. So again, no, if it is the same direction, positive. If it is opposite directions, then it will be negative. And to add to this, work is a scalar quantity, even though it is dependent upon vector quantities. It is interesting that it is a scalar quantity because it is a product of both vector quantities. So the unit of work is in joule. So joule is just 1 Newton per meter. Oh, sorry, not 1 Newton per meter, but 1 Newton times meter. So we have Newton meter, and then we can also write this as kilogram meter squared per second squared. Okay, so we have a conceptual quiz here, no? A quick quiz. So the gravitational force exerted by the sun of the Earth pulls the Earth in an orbit around the sun. Let us assume that the orbit is perfectly circular. The work done by the gravitational force during a short time interval in which the Earth moves through a displacement in its orbital path is what? Okay. So the gravitational force exerted by the sun is let's just draw this down. So let's say the sun is this, and then the Earth is this, right? So the orbit of the Earth will be circular. So we have this orbit, no? Assume that it is a circle. So what is the force exerted by the sun to the Earth? So due to gravitational forces, it will attract, no? It will attract the Earth. So the direction of the force will be into the sun, right? So the question here is, what is the work done by the gravitational force during a short time interval in which the Earth goes through a displacement in its orbital path? So what do we mean by a short interval? So meaning it is about a straight line. If it is a short displacement, so that is about this. So we have this delta R and we have this force. So as we can see, no, we can actually analyze this as a 90-degree angle, no, approximately 90 degrees. So if that happens, then the formula for work will be force times delta R times cosine 90. So what is cosine 90 degrees? So cosine 90 degrees is equal to 0. Therefore, the work done will be 0. So the answer should be A. So again, if the direction or the displacement, no, is perpendicular to the force exerted, then the work will be 0. Okay. So another concept quiz. So the figures show four situations in which a force is applied to an object. In all four cases, the force has the same magnitude. Um, and the displacement of the object is to the right and of the same magnitude. Rank the situations in order of the work by the force on the object from most positive to most negative. So we have equal magnitudes with different directions. We have the same displacement. Now, which one has the highest work done? So the highest work done here will be the force that has the parallel. No? So we can imagine the formula here is work is equal to the force times delta R multiplied by cosine theta. So the cosine theta, the highest value of cosine theta will be 1. No? So the range of cosine theta will be in between in between 0 and 1. So the theta that will make this 1 is actually 0 degrees. So the one that is parallel to your direction of displacement will have the highest. So this should be C as the highest. And then the second one we have that we have here. So everything is either negative or 0. Okay, so let's look at this and this and this. So which one of them has the highest, no, of these three? So this one will be negative since they are opposite. Okay, and actually this one is 0. So the work done will be 0 since this is 90 degrees. So again, no, from the last or the previous example, we have 90 degrees. So therefore, this will be 0. Therefore, this will be the next one. So this will be the second. So we have A. And then comparing these two guys. So which of them has the highest theta? So since this will have a higher magnitude, no, the cosine theta of this will be 0. So this will be negative f times delta r compared to this that is about negative f delta r times cosine of some theta. So this should be lower in magnitude, or the work of this will be much lower than, or I mean, not really lower, no, but the magnitude is lower, but in the number line, this will be off to the left. Ano? So the higher one here from B and D should be actually D. No? So D and then we have B. So if we show this in a number line, we just imagine here this so if this is 0, so the work done here is number line. So the C here will be somewhere here. And then the A here will be this 0. And then the D here will be somewhere here in the negative, no? And then B here will be way off than D. Okay? So C is the highest since it is the most positive. Okay. So another example here, a man cleaning the floor, puts a vacuum cleaner with the force magnitude F is equal to 50.0 newtons at an angle of 30 degrees. With horizontal. Calculate the work done by the force on the vacuum cleaner as the vacuum cleaner is placed 3 meters to the right. So you are, let's say you are this person that is vacuuming something. So you have to pull, you have to pull your vacuum cleaner. Therefore, there is a force that you exerted and then there is a displacement. So it is defined that the displacement here, no, let's say from this point to this point, you have 3.0 meters. And then the force applied will be assumed to be constant, no? So 50 newtons. So therefore, the work done here will be just force times delta R times cosine theta. So cosine theta, we have 30 degrees. So the force is given, the displacement is given, the angle is given. It is very simple. No? So 50 times, we have 3, and then cosine and 30 degrees. So the work done here is, this will be approximately 130 joules. Okay, so that's it. It is that simple. Okay, next one. So we know that previously, no, in our vector topic, that if we have vectors A and B, the dot product of vectors A and B will be equal to AB times cosine theta. I hope you can remember this. So the dot product of vectors A and B will be equal to AB, so meaning that is the magnitude of the vectors or the length of the vectors times cosine theta. And as you can see here, they have the similar format, no? So let's say this is A, this is B, and you have cosine theta. So therefore, the work can be also rewritten as a dot product of two vectors, no, which are the force vector and the displacement vector. Therefore, what we can do is perform the dot product, no, if two vectors are given. So a particle moving in xy plane undergoes a displacement given by the r. Okay, as a constant force acts on particle. Calculate the work done by F on the particle. So again, the work done is just dot product, no? The dot product of your force and your displacement. Therefore, the force here is this. The displacement is this. So therefore, the product is the multiplication of this. So we have 10, okay, plus we have 3 times 2, which is 6. So the unit will be Newton and meters, or meters and Newton. So this will be Newton meter or joules. Okay, so this will be 10 plus 6. So the answer should be 60 joules. Very simple, very easy. Okay. So now let's discuss. Now we have discussed the work done by a constant force. Now, what if the force is varying through time? So instead of just multiplying the force and the displacement, we should consider the variation of the force. So actually, for constant forces, I'll just write down here a representation of work done by constant force. So if this is the constant force axis, so Fx, and then the displacement axis, for example, only in the horizontal. So the work done by a constant force, so if this is your force, okay, this is your constant force through, let's say this is xi. Actually, we can start with a non-zero, let's say from this point. So let's say this is your xi. And you have a constant force from this, okay, until the final displacement or the final position xf. So the work done by this work done will actually be just a multiplication of how high, so the area of this rectangle. So since this is constant, this will be just constant, and then it will be enclosed by this. So the work done by this object is just the area, which is what? So we have the force. This is the work, the force times the x minus xi, which is basically just the displacement, delta x, or in general, for 2 dimensions, this will be called as delta r. So for this case, this is work done by constant force. Work done by constant force. Now, for varying forces, if force is varying, so as you can see, there is a variation here. To find the work done on this particle, then we should consider using calculus, to find the area. So to find this area, since we have the limits, the initial position and the final position, and then the function of the force, which is usually a function of the x, usually lang, no? So the work done on this particle through varying forces, no? So varying force will be equal to the integral, no, from xi to xf of f of x dx. So this is thus just the simplest way to represent this. But we can also represent this as the summation of the work. So if more than one force is actuated on that particle, then this should be the summation of forces in x, no? And then if also the magnitude and the direction of the force is varying, so if the force is varying or multiple forces is changing directions, and also the displacement is in 2 dimensions, then we should consider a general case here, that is the summation of or the net force F multiplied by dr. So dr means the direction in both x and y. So instead of just, I'll just write this down here, no? So basically means that we have x and y here. The r here is just the hypotenuse. You can imagine. For the components, we have, if this is a vector, we have the r vector is just xi plus yj. Okay, so we can utilize this formula for defining work. Now, the ext just basically means that it is done by an external force. So the work done on a particle, is positive. So we should consider that, no? Provided that it is work done by an external object. Okay, sige, let's discuss this now. No? So a force acting on a particle varies with x as shown in the figure. Calculate the work done by the force on the particle as it moves from x equal to 0 and x equal to 6.0. Okay, so how do we do this now? We want to find the total work done, right? So the definition to work done, if we have a plot of your force versus the displacement x, then the work is just the area. Area in a force versus displacement diagram. Okay, so therefore, if this is just a constant force here, then this will be just a rectangle, and then we have a triangle here. So to find the work here, this will be equal to the work done by this first force, this constant force, and then this varying force. So we have work 1 plus work 2. So work 1 is equal to what? So the area of this. So we have a height of 5 and a length of 4. So this will be 5 times 4, which is 20. And then we have here the area of this triangle. So we have a height of 5. So what is the length here? 2. So we have 1/2 of 5 times 2. So this will be just cancelled out. So the answer is 20 plus 5, right? So the answer here, the work is 25 Newton meter or joules. So this will be your final answer. It is that simple. So we have a case here, no, that that is also a varying force. If you have a scenario wherein you attach a block of mass on a block with a frictionless spring, and then the horizontal surface is frictionless and also massless. Sorry, the spring is also massless. Then we can find the total work done by the spring. Okay, so let's consider one thing first, that the force done by the spring is equal to negative of k times x, which is also your displacement from the equilibrium. So what is this? This is called the Hooke's law, no? So this is called the Hooke's law. Hooke's law, which relates the displacement of your object against the force exerted by the spring. So why is there a negative sign here? So there is a negative sign here because if, let's say, the original position or the equilibrium position is x equal to 0, meaning there is no force done by the spring at this position. So if it, let's say it is pulled at this position, then the displacement will be positive since it is going to the right. But the force done by the spring will be negative. So that is why it is negative, because they are opposite in what do you call this? Because their direction are opposite. That is why. So that is the Hooke's law. And to find the work done by a spring, if you can remember, so the work done by an external agent is equal to, or actually just work done na lang, no? Is equal to the integral of the fx dx, from xi to xf. So what is fx here? So fx here is actually the force done by the spring, which is fs. You can substitute this to our integral, and if you evaluate this integral, you will have this. Okay? It is that simple, right? So this can get a little bit confusing if we want to find the work done by an external force. So from this system, if you can imagine, no, let's say for example, you have this block and the spring at equilibrium position. So meaning it is at rest, it is not moving, so it is in its equilibrium position. So if you try to push, no, if you push this spring and this block, so it will be here and the spring here will be compressed, right? So the force that you applied will be in that direction, no, to the left. But as you can see, what will happen to the string if you let go? If you let go, the spring will relieve its stress. So the displacement of that will be going to the right. So since the force applied is to the left and the displacement is to the right, then the work done by an external force will be the negative, no? Kasi nga, if this is your spring, work done by your spring, then the opposite applied force will be negative of that. So the negative of negative kx will be positive kx. Therefore, if you evaluate this integral, you have this. Okay, so there is difference between the two. They have the same, they have similar formula, but it depends on the wording, no? If it is done by an external agent, which is you, and the force done by the spring. Okay, so we have here a conceptual example. So a dart is inserted on a spring-loaded gun by pushing the string by a distance x. For the next loading, the spring is compressed at a distance 2x. How much work is required to load the second dart compared with that to the first? So you can imagine you have this toy gun. So it might look like this, maybe not exactly, but so your gun has a spring, right? So there's a spring inside that, and let's say in order to load that, you have to put something. No? So this is your bullet. So if you compress that to some distance, so let's say the distance here is this. So let's say this is your initial distance, which is your x. Sorry, not compression distance, no? Okay, distance is this. So the distance here from this point, no, this bullet here is compressed. So this will be your distance x. And after that, what you can do is you can compress it on a much higher scale, no? So this will be, let's say, your 2x. So this is x again. So the combination of this is 2x. So the comparison here is how does it relate with your force, or how much force that will you need compared to the first one. So we know that the force of the spring is equal to negative kx. Okay. Therefore, if you have x here, and then the second scenario will be we should multiply this by, actually this is work pala, no? Not force. Sorry. So what we are fighting for is the work. So for the initial case, we have work is equal to, so work external is equal to kxf squared over 2 minus kxi squared over 2. So the kxi is 0, no? Since the initial displacement is 0, no? So the distance covered is also xf. So xf is equal to b or equal to x. So if this is true, then we have kx squared over 2 as our work. Now, what we can do, no, for the second case is that instead of just x, what we do is multiply this by 2. So what will happen to the force? So sorry, the work. This will become 4kx over 2. Okay, so we can cancel this. This will become 2kx squared. So what happened, no, if we compare these two, it doubled. Oh, sorry, it quadrupled, right? So it multiplied by a magnitude of 4. So the answer should be 4. So we will need 4 times as much force, or 4 times as much work to displace that bullet, no, from x to 2x. Yeah. Okay, so a common technique used to measure the force constraint of spring is demonstrated by a setup figure. The sprung is hung vertically and an object of mass m is attached to its lower end. Under the action of a load mg, the spring stretches a distance d from its equilibrium position. So if a spring stretched 2.0 centimeters by a suspended object having a mass of 55 or 0.55 kilograms, what is the force constant for the string? So what is the force constant? So the force constant is actually your K. So what is the given here? We have a given displacement, we have a given mass. So what should we do here? So utilizing the free body diagram that is shown here. So therefore, your force of the spring is positive, and then the weight will be negative. And then since this is not moving anymore, it is in equilibrium. Not really in equilibrium in a sense that the spring is in equilibrium. It is not moving. There's no acceleration. So the summation of forces should be zero. So summation of y is equal to zero. So we have Fs minus Mg is equal to zero. Now, we know that Fs is equal to what? So we have negative Kx is equal to Mg, right? Is equal to zero. So therefore, we simplify this. We want to solve for K. So transpose this and then divide by negative x. So we have K is equal to positive Mg over negative x, right? So the mass here is 0.55. The gravity is 9.8. And then the negative of x. So since the distance here is going downwards, what we can do here, or actually, should it be positive or negative? It should be negative, no? So this should be negative. Actually, the K should be positive all the time, no? So that is one thing we should remember all the time. This should be 2.0. So you should take note of the units, no? So we want to have a unit of Newton meter. So for the force, this will be newtons. So we should convert everything to kilograms and meter and then seconds squared. So since this is in centimeters, so 2.0 centimeters is actually equal to 0.02 meters, right? So this will be 0.02 meters. So simplifying this, what we have here, so negative, right? So this will become positive. So we have 2. What do you have here? So let's just use a calculator. So we have 0.55 times 9.8 and then 0.0. So 269.75. 269.5. So what is the unit? So the unit here, we can have a unit analysis. So we have kilogram, we have meter per second squared. This will be meter. So what happened? Or what we can do now in a much simpler way, this mg is the total here is Newton, no? So this will be Newton per meter. Yeah. It should be Newton per meter, the force constant. Okay, so how much work is done by the spring on an object as it stretches to this distance? So how do we do this now? The work done by the spring on the object as it stretches to this distance. So as it stretches to this distance, what is the direction of the force of the spring? So you can imagine that from this point, the direction of the force of the spring is upward. Meanwhile, your displacement, the displacement x is negative. So this is negative, this is positive. Therefore, the work done should be negative expectedly. So the work done by the spring, which is equal to kxi squared over 2 minus kxf squared over 2, that will be equal to what? So this will be 0. We know that this is 0, right? And then we have negative 269.5 Newton per meter. And then we have xf, so we have negative xf, so this is what is the value? 0.02, right? Meters. And then all over 2. Yeah. right? And that's squared, sorry, squared. So as you can see, this will become negative. So this will become positive if we square this, but still it will be negative after that. So let's compute this using our calculator. So we have 269.5 times negative 0.02 squared over 2. And then multiplied by a negative sign. So we have 0.0539. So negative 0.0539. So what is the unit? So this should be in, so Newton meters. So this will become is Newton meter multiplied by meter squared. So cancel this. So this will be Newton meter or joules. That's it. Next one, so evaluate the work done by the gravitational force on the object. So how do we do this now? So the work done by the gravitational force, so we have the force. The force of the object here is always going downward, so it is a constant force. And then the displacement is also downward. So we can find that the work here is just the force times the displacement. So they are in parallel, which is cosine theta. So this will be equal to, so the gravity mg, delta r is just the displacement here is, we have xf minus xi. And then cosine theta. So theta here is 90 degrees. Sorry, zero. Okay, anyways. So M is given 0.55. G is 9.8. So XF is negative. Oh, it should be negative, right? Oh, so this should be, okay, a convention nga pala, no, this should be negative. If the force is negative, if this is positive, so this should be negative, right? Okay, so, okay. So we have negative 0.02. Yeah. Okay, that's it. So the angle here is, since this is, so they are parallel, so angle is equal to 0. So 0 degrees. So therefore, this will be equal to uh, negative 0.55 and then 9.8, and then we have negative 0.02 minus 0 and then cosine 0. So the work done by the gravity, okay, I'll just write here some G. So negative 0.55 times 9.8 times negative 0.02 cosine 0. So we have 0.0178. So the 0.1078. So joules, that will be the answer. All right. So we're done with work. Now let's discuss kinetic energy and the work kinetic energy theorem. So a result of doing work, so if you do work, then the object has moved from one place to another. Therefore, there should be a change in velocity from point A to point B, right? So let's say it started from rest. If you put force in it, then it will have a velocity and it will have also a displacement. And that velocity, no? So there is an energy transfer from you to that particle. So let's say you pulled an object from this distance, no? Then you gave that object kinetic energy since it will have a higher velocity from what it has before. So kinetic energy is defined as 1/2 times the mass of this particle times the velocity squared. Or actually, this is the speed, no? To be specific, this is speed. So meaning this is the magnitude of velocity. Okay, so remember this as well. So for calculating work, if we simplify this, actually, we don't have much time. I won't discuss this anymore. But we can derive the work done by this change in velocity as the change in kinetic energy. That is the difference between the kinetic energies in the final point versus the initial point, or or again the change in kinetic energies in this form as well. So this relationship, the work done on the object and the change in kinetic energy is called the work kinetic energy theorem. So now let's have an example here that shows this or showcases this work kinetic energy theorem. So a 6 kilogram block initially at rest is pulled to the right along a frictionless horizontal surface by a constant horizontal force of magnitude 12 n. Find the block speed after it is moved a horizontal distance of 3 meters. Okay. So regarding this block, we have here a force applied, and then we still have forces here, but the problem with these forces is that they are 90 degrees with the distance or the displacement of your block or your particle. Therefore, we can just neglect these forces. So the work done by this object is equal to the change in the kinetic energy, right? So this is just the change in the kinetic energy, which is equal to 1/2 times the mass times the final velocity squared minus mass times the initial velocity squared, and then also the 1/2. I forgot the 1/2. Now, how do we find the work here if we have a given distance and a given force and a given mass? So this work is also actually equal to the force times the displacement x. Okay, so we can write this as 1/2 mv f squared minus 1/2 mv I squared, which is equal to this. So we can just make this general, no, r and then cosine theta. But since we know that the angle is the same, so that they are parallel, therefore the angle is 0. So remember that the parallel, if it is parallel, then angle is 0 degrees. Okay, remember that. So therefore cosine 0 is equal to 1. So we can just omit this as 1. So we only have f times delta r. You can write this as delta x as well if you want, but I'll just write here delta r for now. So the distance here is 3 meters and the magnitude is 12 newtons. So we have that given. The mass is also given. So initially at rest, so the initial velocity is 0. So we can find the final velocity. So we have f delta r is equal to 1/2 mv f squared. So rearranging this, we have vf squared is equal to f delta r times 2 over m, right? So vf is equal to the square root of 2f delta r over m. So substituting the values, we have 2 times 12 times 3 over m. So the mass is 6. So take note of the units, okay? So they should be all in Newton kilogram and meters. Okay, very good. So the final velocity should be about 3.5 meter per second. So this will be your final velocity. So upon applying this force, we have a work done. We have a change in kinetic energy. So the final velocity will be 3.5 meter per second. Okay. So a man wishes to load the refrigerator onto a truck using a ramp at an angle theta. As shown in the figure, he claims that the less work would be required to load truck if the length L of the ramp to increase so that the angle theta will be smaller. Is his claim valid? Okay, so someone is trying to put their refrigerator into this pickup truck, and the claim here is that if you make the length L longer, so meaning if you make the ramp longer, okay, thereby so the angle will be smaller. So this will be smaller. Or let's say this is alpha. This will be much smaller than theta. Then the work should be, or less work will be required. So now how do we do this? No? So what is stopping us? No, the question here is what is stopping us from loading this refrigerator to the truck? So we have this height, diba? So the height here is our constraint. That's why we need to use this ramp. So basically, we just need to lift this truck upwards, and we will have, or we can put this truck in, sorry, we can put this refrigerator in this truck. So therefore, what we can do, or what we are trying to counter here is the weight, or the work of the gravity. So the work of the gravity is the mass, no, times what? Actually, we can derive for the mgh later, no? But the total work that we need to do, which is also equal to 0, is equal to, so I think this is just mgh na lang. I'll just discuss this later. It is much harder to discuss if uh, I will use the angle, no? But the work that we need to counter is just the height. No? So the weight, the force here is this weight. So we have the force, and then we have the height. So the height should be upwards. So therefore, this actually should be negative, no? So the work done by the gravity is negative. So therefore, the work that we need to do, that the man needs to counter, is just the opposite of this. So this will be just mgh. So is the ramp, or the length of the ramp, or does the length of the ramp affect the work done, to put this in the truck? So the answer is no, since it is only dependent with the height and the mass of the refrigerator as well as the gravity. Therefore, the answer is, if it is claims valid, the answer is no. Okay, so now let's discuss the potential energies. So we have the gravitational potential energy and the elastic potential energy. So for the gravitational potential energy, we have UG is equal to mgy, and US is equal to 1 kx squared. So the gravitational potential energy is just how much potential energy can be stored based on its height. So you can imagine, if you have a ball that is much higher, it will have a higher terminal velocity, or a final velocity, as it hits the ground, compared to a lower ball. No? So if you compare these two balls, you have these two balls, for example. So this one will yield a higher potential energy, that is the gravitation energy, compared to this one. So the height basically is a measure of the gravitational potential energy. So you can imagine that you can convert this potential energy into kinetic energy once you let go of this ball. So it will have a terminal velocity here, which is also your final velocity. So the change in, or the work, uh, the work done by this potential energy will be actually the difference between the initial and the final potential energies. So assuming that there is so in this context, this is assuming that there is no what do you call this? No change in, or no initial velocity na lang, no? No initial velocity. Anyways, I will not try this now for now. Sorry. Okay, I'm really tired now. So, sige, let's move on. So, the elastic potential energy is another way to describe this potential. So, you can imagine a spring and a block, and then let's say you push your block to your spring. So, you can store some energy, no? So, this will be your spring compressed. And if you let go of that block, it will oscillate, no? Or it will push that block towards to the right. So there is a potential energy that can be converted as well into kinetic energy. So this elastic potential energy is just force times actually the force times the displacement x, so that the elastic potential energy is just negative kx times x, so this will be kx squared. So the elastic potential energy is or the work done by this elastic potential energy is the difference between the initial potential energy and the final potential energy, which is described as this. Okay, so that's it. So choose the correct answer. The gravitational potential energy of the system is always positive, always negative, can be positive or negative. So what is that? So actually, when you define your gravitational potential energy, so let's say you have this ground, no? And let's say you have a ball, no? So if you have this ball and then it's dropped to the ground, then you have a change of from potential energy to kinetic energy, right? So the potential energy of this will be mgyf. And mgy, wherein y is just the height. But we have to remember that there is reference to distances. So this ground here will be y is equal to 0. Therefore, the y values upwards of y is equal to 0 will be positive, and the values of y below y will be negative. So therefore, if let's say, we can imagine a scenario wherein we have, let's say, a deep well, then therefore we have let's say we have a ball here, somewhere here. So the distance between this y is equal to 0 and that will be negative. So therefore your mgy will be negative. No? So the potential energy with respect to its gravity will be negative. So it could be either positive or it could be negative. So the answer should be C. So depending on the position or depending on your reference, so it could either be positive or negative. So we have here a trophy shown off by a careless athlete slips from the athlete's hands and drops on his foot. So choosing floor level as y equals to 0 point of your coordinate system, estimate the change in gravitational potential energy of the trophy earth system as the trophy falls. Repeat the calculation using the top of the athlete's head as the origin of the coordinate. So where's the no? Oh, I don't have the figure. No, I don't have the figure here. So okay, sorry, no. So we don't have the figure, but we have a given, no. So sorry, I didn't have the figure. I think I erased it or something. So the mass here is 2 kilograms. I'll just write down the given. And then, this is a disaster. No? Huh. So the graph here is, we have, where is that? So the athlete, we have to say this is the athlete, this is the trophy. So the athlete's foot is about this high. So we have a height here, and then the ground here. Sorry guys, no, I did not include the figure. Unfortunately, so we have an initial height that is, if this is y is equal to 0, then there should be, what is this? 1.4 meters. And then it drops off here in his or her foot. So we have a height as well here that is 0.05 meters. So we have to find the change in potential energy. No? So the change in potential energy, okay, that is equal to mgyf minus mgyi. So we can actually factor the m, no? We have mg actually. Mg and then yf minus yi. So we have given. So this will be equal to, we have 2 kilograms, so 2 times 9.8. And then we have 1.4 minus 0.05. So this will be equal to about negative 26.4 joules. So this will be your change in, actually it's not US but UG. So this will be your change in gravitational potential energy. Now let's repeat the calculation, and instead of using the ground as y is equal to 0, we can use the athlete's head as the origin. So what does that mean? So let's say we have again this athlete holding this trophy. Okay. And then we have his or her foot that is, sorry, no. I'm sorry, I cannot draw a foot. Ayan. Okay. We'll draw a foot here as well. So, we have a given here now. Sorry, I did not write the given. But if this is will be your y is equal to 0, then the distance here is uh 0.6. Okay. And then the distance here for the final position, no, of this trophy will be what do you call this, 1.95. Then therefore this will be negative now. Pag downwards, it should be negative. So finding this again, the change in gravitational potential energy. Okay. So same formulas as last time. So we have 2 times g. So the yf here should be negative. Okay. So we have here the final position is negative 1.95. And then minus the initial position is negative 0.6. So what is the answer here? Okay. So the answer here, ah, what? What happened? I think I have this wrong again. I swapped this. So the final position is 0.05. Sorry. And this should be 1.14. Sorry. So therefore, we can solve this into okay, let's use our calculator. 2 times 9.8 and then negative 1.95. So this will make a positive, so plus 0.06. So the answer should be negative 37 joules. Okay. Huh? I think I did some wrong calculations. 0.06. Sorry. Yeah. Okay, so this will be the same answer. So this is about negative 26.4 as well. So as you can see, if you differ the reference, also the reference here is this ground. And if you change the reference here, this will be, or the changing gravitational potential energy should be the same regardless of the reference. Okay. So for elastic potential energy, you can imagine or well the translation or the changes in or the exchanges of energies throughout a mass and a spring setup. If you put your mass or you compress the spring initially and then you release your hand, no? So initially you stored potential energy, which is also the total energy. So this is a stress. If you let go, no, after you let go, it will have this velocity. So some of that energy totally is converted into kinetic energy. Some will be left as potential energy, and then and so on. So at maximum displacement, or after it has transferred all of its energy or potential energy, it can be converted into kinetic energy. So the total energy will remain the same regardless of this. So assuming that it is an isolated system. Yeah. I think this is the last one. So a quick ball is connected to a light spring suspended vertically as shown in the figure. When pulled downward from its equilibrium position and released, the ball oscillates up and down. In the system of the ball, the spring and the earth, what forms of energy are during the motion? So kinetic energy, and elastic potential energy, kinetic energy, gravitational potential energy, kinetic and elastic gravitational energy. So in this system, we have involved or the ball, the spring, and the earth. So meaning the ball is pulled by the spring and it is also affected by the force of gravity. So if you release this, there will be a velocity, no, upwards. and it will oscillate back and forth, right? So there is a total energy. So the total energy here should be a sum of its kinetic energy and then its potential energy or gravitational potential energy and its elastic potential energy. So we should include all. So the answer should be C. Sorry. Why is that? Huh? Sorry. Oh, so the answer is C. Yeah. The answer should be C. And then in the system of the ball in the spring, what forms of energy are there during the motion? Choose from the same possibilities A through D. So for this case, if we have this case, so therefore we don't have gravity. So basically there is no gravity. So the only forces involved here are the force of the spring. That's it. And there will be a velocity incorporated with that. No? So there will be a change in velocity that in there. So the total energy will be equal to the, the the potential energy of the spring, so elastic, sorry, S, and then plus the kinetic energy. So the answer should be A, okay, for this number. So that's it. So thank you guys for listening. I hope you learned something here, and please answer the exercise that I have prepared and then prepare for a quiz next week. So that's it. Thank you guys, and good night. Okay.